Good day and welcome to part one of our discussion on differentiating exponential functions. In this first part of the discussion, we are going to solely focus in on basic properties of the exponential functions so that we can make use of them later on when we need them for more calculus-related properties. So with that in mind, let's go ahead and define an exponential function. An exponential function is a function that has a very specific form. And that form would be a to the x. A is a constant, which we would refer to as the base of the exponential function, and we have the stipulation that a is a positive quantity. Now, when it comes to visualizing an exponential graphically, there are three main cases for us to consider. There's a case where the a value is strictly between 0 and 1, the case where the a value is 1, or the remaining case when that base value a is strictly larger than 1. And let's just go through and sketch these one by one. The simplest case is in the middle. When a is equal to 1, our function is simply y equals 1 to the x, and 1 raised to any power is 1. So in that sense, we get an awfully boring graph for our exponential function. It is the horizontal line y equals 1, and it has a y-intercept of 1. In the case where a is between 0 and 1, the exponential function, as you might expect, will be decreasing. Graphically, it looks something along these lines, and it also has an y-intercept of 1. So this is a graph of y equals a to the x, when a is between 0 and 1. When a is larger than 1, we get a similar looking graph, but it would be the case where we have exponential growth. So roughly speaking, something along these lines. And once again, we have this y-intercept of 1. And a few properties related to these. In the first case, when the a value is between 0 and 1, we have exponential decay. So in this case, we can very easily observe from the graph that it's a decreasing function. And there's two limits of interest. There's kind of what happens way to the right and what happens way to the left. So note the limit as x approaches infinity of a to the x, that is what happens for very large and positive inputs, is 0. And the limit as x approaches minus infinity, that is what happens for very large and negative inputs, the function outputs are blowing up. They're going to positive infinity. And then we can make the similar observations when a is greater than 1. The function is increasing. The limit as we approach infinity of a to the x is infinity, and the limit as x approaches minus infinity of a to the x would be equal to 0. So continuing on with the basic properties, as long as a is positive and a is not equal to 1, so we're kind of ruling out this middle case, mainly because it's really not that interesting, then f of x equals a to the x is a continuous function with domain being all possible inputs, and its range is all possible positive outputs. And at this point, before writing down some of the basic properties of the exponential functions that we're all familiar with, let me go back to our definition and kind of pose a question for you to think about. Why do we, and I'll say need in this case, a to be greater than 0? And let me give you a quick but hopefully compelling reason. If a is equal to minus 1, just to pick a specific value, and you look at this function f of x equals minus 1 to the x, on face value there might not be any issues, but let's think of a specific input. If we want to know what f of 1/2 is, that would be minus 1 to the 1/2 power, which is the square root of minus 1. And I agree. How do we work with that? So that is the reason why we need a to be positive. Because when a is negative, you can get these troublesome quantities that we would consider in a more upper level math course. But for now, let's go ahead and explore some of those basic algebraic properties of the exponential functions that you've most likely used over and over again in your pre-calculus experience. So if you have a to the x plus y, properties of exponentials tell us that this is a to the x times a to the y. Similarly, a to the x minus y becomes a to the x over a to the y. And a case that we should be familiar with to go along with this, if you have a to the minus x, note that's 1 over a to the x. Remember, a negative exponent is equivalent to dividing by that quantity with a positive exponent, which, if it's convenient, you can certainly write this as 1 over a to the x. And then a few more properties. If you raise a power to a power, so a to the x, quantity to the y, you multiply together those powers, so a to the xy. And you can also distribute an exponent over a product. So ab raised to the power x can be written as a to the x, b to the x. And note, all of these basic properties can be used in either direction. Going from left to right or from right to left, depending upon what is more convenient for your current algebraic manipulation. So let's finish up our discussion by getting back to a familiar calculus problem, which is evaluating a limit. But before diving into this specific example, I should probably make an observation just to make sure we're all on the same page. So this number e is defined to be 2.71828 ... It's an irrational number, which essentially just indicates it has this infinite decimal expansion to it with no kind of nice repeating pattern. Now, one more detail before diving into this limit, we might want to think kind of graphically, what of the cases above does this function e to the 2x fit into? Well, in order to determine that, we need to write it in this form, a number raised to the power x. And if we look at our third bullet above, a to the xy can be written as a to the x to the y. And with that in mind, we could make the observation that e to the 2x can be written as e squared to the x. And now this has the form of an exponential function. We have our a value equals e squared, which is most certainly greater than 1. So we're in the case of having this exponential increasing function, which approaches infinity as you go to infinity. So intuitively, if we think what this function is doing as we approach infinity, the top is going to infinity and the bottom is going to infinity. And with that in mind, what is infinity over infinity? And if you are unsure how to answer that question, you are in good company, because infinity over infinity is a quantity that we cannot define. It turns out it can be really anything. And this is something that we've seen in the past, and let me give you kind of a quick reminder example from Calculus 1. In Calculus 1, we investigated these infinite limits, and we concentrated quite a bit on rational functions, a polynomial over a polynomial. And this is a similar case. The top goes to infinity, the bottom goes to infinity. And our approach for evaluating this was to multiply by 1 in a fancy way. We would determine the largest power of x in the bottom, so x to the first, and we would multiply by 1 over x divided by 1 over x. Let's go ahead and see if we can do that intuition here. The largest power in the bottom would be this e to the 2x. So let's go ahead and multiply by 1 in this somewhat fancy way. 1 over e to the 2x divided by 1 over e to the 2x. And we're simply following the intuition or the process we came up with in Calculus 1. And when we multiply that through, we have to distribute and hit each term in the bottom. But in the top, it works out extremely conveniently. E to the 2x divided by e to the 2x is 1. In the bottom, you're left with 1 plus 1 over e to the 2x. And now I'm going to go ahead and apply our limit laws. So we can take the limit of the top over the bottom. And when you take the limit in the bottom, remember a limit can be broken up over a sum. So you can write it as the limit of the first times the limit of the second. The first limit on the bottom and the limit on the top are the easy ones for us to evaluate. The limit of a constant is always at constant. But the question remains, what is the value of the limit of this remaining term in the bottom? And let's just write a few details again to the side. 1 over e to the 2x can be written as 1 over e squared raised to the power x, which is an exponential function. And if the a value, the base of the exponential, is 1 over e squared, we have 1 divided by something larger than 1, which is less than 1. So we know, very roughly what the graph of 1 over e to the 2x looks like. It's an exponential function whose base is less than 1. So it's in this first or decreasing case. So as you go to infinity, way out to the right, that function is approaching 0. So what we end up with in this case is 1 over 1 plus 0. The value of this limit is simply 1. And I realize it probably feels as though it's been a while since we've evaluated limits, rightfully so. But we will encounter limits somewhat frequently throughout the remaining of this chapter specifically. In fact, the last section in this chapter is something called L'Hopital's rule, which is all about evaluating limits when you have these so-called undetermined forms, things like infinity over infinity or 0 over 0. So if you're feeling a bit rusty with your limit laws, this would be a great opportunity just to turn back in the book to the section on limit laws and review a few of those basic properties. And of course, if you have questions, feel free to reach out and let me know. Also look at the corresponding suggested problems for this section in the book. In our next video, we will continue on exploring the exponential by thinking about how we can differentiate it. So stay tuned. Take care.